Right.
Okay. Hey, good morning, everyone. Thank you for coming. We're going to kick it off this morning with capacity and stability patterns presented by Brian Pitts. Welcome him on stage.
Hey, so thanks a lot for that introduction. This is going to be a talk on capacity and stability patterns. But before we get into that or get into me, I'd like to ask a few questions and get a show of hands so I kind of have a feel for the audience I'm talking to today. How many people here consider themselves to be primarily software developers? Cool, so most of the room. How many people would say they're primarily systems administrators or operators? All right, a few of us are represented here. How many people don't fall into either of these groups but just want the websites you use to actually work? Yeah. And if I open that up, probably everyone would say that's really what they want. Cool. So, hi, I am Brian Pitts. I work as a systems engineer at Eventbrite in our Nashville office. So I drove up yesterday. This is my first time at Pi, Ohio, and first time in Columbus as an adult. It's been wonderful so far. I'm really looking forward to the rest of the conference and getting to know you and this great city more. So I am Skyrus on Twitter, if you're the sort of person who likes to follow people on Twitter. And I have a website at Polybyte where you'll be able to find these slides after the presentation. So I work as a systems engineer. What does that mean? So what does systems in here mean? So this is an unweighted visualization of software that I took by looking at our configuration management repo and pulling it all out. So this is what powers Eventbrite, and it's a lot of stuff. And my team basically is responsible for the care and feeding of all of these systems and infrastructure. Hopefully there's at least a few things on there that might look familiar, like Python, Sentry, uWhiskey. If Django's not on there, it should be in big, bold letters, because Eventbrite is primarily a Python and primarily a Django shop. Now, what about Eventbrite? The fun thing about talking at tech conferences, I usually don't have to introduce Eventbrite, because if you don't know what Eventbrite is, how did you get your ticket? How did they let you in the door? So we call ourselves as a global marketplace for live events, which is big ambitions. In the last year, we had 600,000 active event organizers, sold over 150 million tickets, and did $2 billion in revenue from those ticket sales. Now, here's the interesting thing about events. Some events are bigger than others. This is a graph of calls to one service endpoint involved in purchasing a ticket. And in Eventbrite vernacular, this shows what we call an on-sale. Just like a sudden, extreme spike in activity due to a popular event going on sale. So a big part of the job for the operators and developers at Eventbrite is designing systems that can cope with this sort of traffic pattern. Now, we are far from perfect at doing this. And this presentation I'm going to give you is far from comprehensive about ways you can tackle this problem. But my hope is that I'm going to give you some concrete ideas you can take to improve your own systems that you're developing and operating. And the patterns I'm going to talk about today generally fall into one of two categories. The first of those is stability, which I'm defining as doing processing, doing work in the face of impulses, stresses, or component failures. And I said this is how I'm defining it, but actually I'm cheating. This is from Michael Nygaard's book, Release It, which is a fantastic book and one of several that I'll recommend throughout the presentation. So in his definition, an impulse is a rapid shock to the system. It's that hockey stick graph that just is chugging along and then goes up, up, up when that event goes on sale. And stress is force applied to a system over time. So maybe that data store you're using that's on a bad disk and has suddenly started dropping in performance by 10%. What's the effect of that over time? So stability is number one. The second category is capacity. And this capacity is the throughput a system can sustain with acceptable response time. And accessible is a key point here. When I've given this talk before, I've got questions about, how do you define capacity? I can throw, 100,000 requests at the system, and they'll come through. But that's not a good way to measure your throughput if that first request only comes through after processing for 5 minutes because you've saturated your resources, and all your users are long gone by then. So it doesn't matter that technically you could sustain 100,000 requests a minute if all of those requests are going to a browser that's already disconnected. So now I'm going to dive into some of the patterns that we've applied here. And after each pattern, this is like in the past, I've had people open up the questions after each pattern, but because this is a big group and I don't want to go over time, I think what we'll do is if you have questions about a pattern or ways we've applied it or thoughts about how you might apply it, if it's like a generally useful question, hold on to it and ask me afterwards. We should have some time. If it's like a more specific about your scenario or you want advice, just come find me afterwards. I'll be here over the next 2 days. And I'm like super happy to geek out over any of the stuff. Otherwise, why would I even be here doing this, right? So, pattern number 1 is bulkheads. The idea behind bulkheads is partitioning systems to prevent cascading failures. So this is a nautical term, which is why I threw up a diagram of a boat up here. So you can see that within the hull of this boat, there are walls separating each compartment of the boat. So if we imagine someone coming up and poking a hole in the hull of that boat, water's going to go in the boat, sure, but it's going to be stopped, right? It's not going to fill the entire boat. Instead, the damage is going to be contained. And this same design that we can apply to building ships is what we want to apply to the infrastructure we run. So let's look at what I think is like the sort of simplest architecture diagram you'll see in like any presentation someone's giving about designing web systems. You're going to have your load balancer in the front that the users talk to. You're going to have a pool of web servers sitting behind that. And those web servers are going to talk to a database where the data actually lives, right? And so right now, we're happily processing requests. You see I've got all my boxes and cylinders, and they're all green. Everything's good. Now, what if some of these requests end up taking much longer than others? Let's say the average request takes a second, but we have some requests that take 5 minutes. Maybe we're generating some very complicated report for an organizer who has lots of events on the system. Well, when the first of the month comes and they decide it's time to go generate all their reports and they start submitting these requests, oh wait, the web servers aren't so happy anymore. The worker processes that were happily chugging along, filling tons of users' requests, are now all busy trying to satisfy these series of reports that came in, and our web servers are overloaded, can't handle other users' requests, and this one user has essentially brought down our entire pool of web servers. Not very cool. So what could we do about this? Well, this is where bulkheads come in handy. So we can imagine having 2 separated pools of web servers, one that is handling the general requests, one that's dedicated to this reporting example I gave you. And so now, yeah, things aren't so great. The reporting web servers are still bogged down, but only the people generating reports get that bad experience. And our regular users trying to create events, purchase tickets, they're still chugging along happily on bulkhead A, while the reporting on bulkhead B, is bogged down. So at Eventbrite, we do this a lot. We have tons of different pools of web servers, and we're routing to them based on URL patterns, the user agents, just different ways to classify our traffic so that we can guarantee quality of service to certain types of requests. Now this bulkhead design pattern applies to stateful services as well. Like in the example I gave you about reports, it would be kind of disingenuous to say, oh, it just bogs down the web server. Probably one reason it's slow is the web server is waiting on this complicated SQL query to return. Well, what if we have a database slave dedicated just to answering those reporting queries and another database slave for serving general traffic? We can make the scope of our bulkhead as large as we need it to be in order to bound the failure cases that we're concerned with. So in this reporting example, now bulkhead B and its database slave are unhappy generating those reports. But again, the other traffic is chugging along just fine. So next, after bulkheads, I'd like to talk a little bit about canary testing. or the gradual rollout of new code. Now, canary testing is fun because it's probably one of the few terms in like software development that we stole from mining. In particular, coal miners used to suffer like pretty terrible deaths from buildup of gases in the mines. Slowly over time, a gas like carbon monoxide could build up. People would not realize it was happening, and they'd be suffering the effects of it, which would make it even worse because you don't notice when you're being poisoned by carbon monoxide. So what they realized they could do as a safeguard is take a canary down into the mines with them. The canary is much more sensitive to the effects of the gases than humans are. So when you're down doing your work, someone is keeping an eye on the canary, and if the canary starts to act strange, or as our poor bird has happened here, keel over, you know that it's time to get out of the mine. So we want to apply this same principle to the code we're developing. We don't want to subject all of our infrastructure and all of our users to the new code at once, because what is the problem? Well, then it's too late. Everyone is going to suffer. Instead, we'll roll out the new code or functionality gradually, see how this gradual limited subset of it does, and then, only then if it looks good and we build confidence after a while, will we finish the rollout. So there's really two ways we do this at Eventbrite. One way is what we call baking releases, and I've thrown up like part of a dashboard that people would be looking at while we're making a release. I intended to show you the whole dashboard, but it turns out I'm like really bad at CSS. So this is all you get. So when we're making a new release, which we do like multiple times a week, sometimes multiple times a day of our core product, it goes out to a set of servers within each of our bulkheads first. And then we'll take a close eye at the health of those servers and compare their health to the other servers for things like response times, error rates, user actions on those servers. Just generally like, does this look okay? And only once we're like, yes, this looks okay, will we finish the kick off the rollout to the rest of the server fleet. The other way we do this canarying is through feature flags. For this, we're using a fork of Gargoyle from Discus, and I show some code here. The basic idea is that new features, or really many different types of changes, when they're released, they're off by default. So enabling a feature, running your new code, which is the risky and scary thing, is not actually coupled to the process of releasing your code. So we see in my example here, we just have a Gargoyle is active check for our cool new feature. If this feature is active, we do it. Otherwise, we keep doing what we were doing before, which we know is safe and performs and works well. So we almost every feature that goes out gets wrapped in some sort of feature flag, and this is like chat script transcript showing how someone might submit a proposal and the flag might get turned on. So a sample rollout might be, first let's turn on this new feature for internal users, like within our offices or on our VPN only. Then maybe if it's something that changes the behavior of the product, opt specific organizers into it who want to beta test it. Then start a ramp up of an increasing percentage of users, 10%, 20%, 50%. Finally, take it global so everyone gets a new code or new experience. And the actual ramp-up process will vary depending on what the feature is and how risky it is, what's actually changing. But the idea is, if at any point it turns out, oops, hey, a new error popped up, or oops, wow, this got a lot slower, we don't have to do any rollbacks. This could be weeks into the process we discover a problem. We can just turn it right off instantly. So next, after feature flags, let's talk about graceful degradation. This is turning functionality off in response to failures or load. So on a site like Eventbrite, and probably most of the sites that web developers here would work on, some functionality is more critical than others. We care a lot more about someone being able to create an event or purchase a ticket than we care about someone getting recommendations for events they might want to check out, for instance. We tend to do a lot of graceful degradation through our feature flagging framework, which is not the most sophisticated way to do it, but it's something that's worked out okay for us. So an example might be doing in response to failures. So in the dark old days, we used to run MongoDB for page view tracking and like some reporting features based on top of that. So organizers could see like how many people came to their event on different days through different channels. If MongoDB went belly up, we had a long-lived feature flag we could go in and turn on, just like disable page view tracking. And so instead of servers waiting to talk to MongoDB and getting errors back, they just stopped doing that. Another example would be turning off recommendations during some of our larger on-sales. So now, like, our recommendations are generally served by Ajax and have like a dedicated set of resources to it. But in the past, the recommendations used to be generated like in line with the event page. And so if we wanted to have like maximum capacity for people to show up to an event page and purchase events, we'd like to avoid doing the work and extra CPU time and request time it took to generate those recommendations. So if we were worried about that, we could just go and flip a flag. Recommendations would just stop showing up at the bottom of event pages. There's been some development, some experimentation at automating some of this work. We have a tool internally we call the velocity engine that right now we primarily use for like fraud purposes, like tracking rates of actions across the site. And one thing people have played with is also piping certain types of errors through there. So we can say, hey, if this sort of error comes through, turn off this flag. Or, hey, we detect, based on rate of certain events, we're in like a high volume situation right now. We want to conserve resources. Here's some optional functionality. Just turn it off automatically. So we're sort of playing with that to see if it's worth it or not. Kind of related to graceful degradation is load shedding. Now, in load shedding, you're purposefully not handling some requests in order to reserve resources for others. So what's different and compared to graceful degradation is with load shedding, instead of serving like a more limited experience to all users, you actually serve a completely different experience to users depending on if they've been shed or not. For us, the primary example of this is what we call our waiting room. So doing a very large on-sale, we don't want to have to over-provision to the extent that we could literally handle 100,000 people placing orders at once. That would be like prohibitively expensive for us to do for the amount of times we need to do that. So instead what happens is we have a system where after a certain number of users have entered the order flow for an event, any additional users coming through aren't allowed to enter that flow. Instead, they get redirected to a totally different set of systems, different load balancers, web servers, like decoupled from the main site, main order processing flow, that simply says, hey, you're in line. As soon as your spot is ready, we'll send you back into the order flow. Until then, just sort of chill out here. And so this is like a really critical way we have to sort of protect the site and keep up and running, even when that 100,000 people do show up. And you still get a good experience. Like, you showed up on the page. It's not just spinning forever. You're not just hitting refresh, like, can I get in, can I get in? Which, when your customers do that, this decreases your load, makes it even worse. You get a nice message sort of explaining what's happening. And then when you're ready, you get put through the order flow. We also do this occasionally just in terrible emergencies. Let's say something wasn't load tested properly and maybe a really bad query snuck out. And there's no way we can handle traffic to a certain feature or a certain event that's going on right now. We might just literally go into our load balancers at the edge and just block that event. Say, before it hits anything that actually runs Eventbrite code, like return an error response, say, we're sorry, this page is unavailable to you. So that's an extreme measure, but a way to give people a really bad experience, which you don't want to do, but you do if it means protecting the experience of everyone else. So next is rate limiting, which I'm defining as controlling the amount of work you accept. So the idea here is you want to understand the capacity you have and prevent exceeding it, because it's better to fail fast and give your caller a message that the limit was exceeded, then cause cascading failures because your system is overloaded. The callers of your system are now bogged down and overloaded, waiting to talk to you. Callers of them are now bogged down and waiting. And an excess of work and overdoing capacity in one area can quickly sort of cascade beyond that and take down lots of systems that you might not even realize are related. So it's better to not accept that work than to say, yep, just wait, I'm going to give you a response. And then they wait, and they wait, and they wait, and the errors start to propagate. So we do this in a few different places. At the very edge of our infrastructure, we have some rate limiting in IP tables and in Nginx as well, just to catch like extreme cases. Like, no, wait, one IP address shouldn't show up and start submitting like 1,000 queries a second. Like, that's just not legit. Let's just block that flat out. We do this some in our application where we have like more smarts. We can make better judgments about the requests that are coming in and do we want to handle them or not. Although, truthfully, right now, most of the stuff in the application is more centered around handling and preventing abuse than it is around protecting the systems. And you really want to be sure and have this anywhere there's a queue within your system. Or, if you're using external or like third-party systems, if they have queues as well, find ways to limit them. An example of some software that does this really well is Elasticsearch, for instance. And I'll give the pitch now. My coworker, John Berryman, is giving a cool talk on Elasticsearch tomorrow you should check out. But one thing that's wonderful about it from an operator's perspective is for every operation you can do in Elasticsearch, a search operation, an index operation, it has a bounded queue, the amount of work it will accept. And beyond that, it immediately rejects your work, which is great because that means you don't get to dump 100,000 requests in there and then have 100,000 processes waiting for a response it's not going to get. You can only dump, say, 1,000 requests in there, and beyond that, immediate failure, which you client code can then understand and handle instead of waiting and causing those cascading failures. So kind of the flip side to rate limiting would be timeouts. So timeouts are limiting the time that you will wait for a request to complete. So rate limiting was on the receiver's side. The timeout is basically the same idea, but it's on the sender's side. And it's the same underlying principle that, again, it's better to fail fast than wait and contribute to cascading failures. So again, like rate limiting, there's like lots of levels you can apply this at. So at the edge, we'll have just like general timeouts, like on requests to web servers. And then internally, as we have different servers handling requests, just timeouts on how long they would wait to talk to the next tier of those web servers or load balancers. We'd have timeouts on requests to data stores as well. For example, like if you ever have to wait longer than a second to get your answer back from Redis, like something is horribly, terribly wrong, you probably just shouldn't be waiting. So just cap it at a second. And crucially, you want timeouts on any calls you're making remotely to systems that aren't under your control. So a great example for us at Eventbrite is our webhook system. Organizers can register to say, whenever someone purchases a ticket to my event, I want you to ping information about that to my web server. There's all sorts of events they can subscribe to. Now, what if they haven't heard this presentation and applied these lessons, and their web server goes down? We don't want our webhook system to be tied up, waiting on requests to return to some web server that has been crashed by the load of the webhooks it's received from us, right? So we need timeouts there to ensure that the other webhooks don't get bottlenecked behind those failing ones so that those webhooks can properly fail after a few seconds, and then other webhooks for other organizers can keep flowing through. Okay. Next would be caching, the idea of saving and reserving results to reduce expensive requests. And it's kind of a tricky one, but it's a powerful one. So at Eventbrite, it tends to take one of two forms. We're saving like computed values from within our code base in either a memcached or Redis, because we have both because reasons. Or you can save an entire HTTP response and serve that back. Not do any work in your application. And for us, we do this a lot with Varnish. There's other caching proxies like Squid can do it for you. Nginx even has some limited capabilities. This is like the holy grail if you can do this right. Not even touch your slow application code. Okay, maybe I should back up. Python doesn't have to be slow, but it might be slow. So if you can run it in some fancy fast C code and just spit back the pre-computed result, like that is really keen. But it's also tricky, right? Because are you sending back the right result? When you're doing caching, you've got to think about invalidation strategies. And this probably deserves its very own slide, so it has one. So there's like a few ideas that we've played with this at Eventbrite, and this evolved over time. Like the first idea was just your TTLs need to follow the KISS principle of keep it short, stupid. So if you imagine that hockey stick-shaped graph I showed you earlier, if we were caching something for even 5 seconds, that could make an enormous difference in the amount of requests that we had to actually handle. So that was actually like the genesis of most caching in Eventbrite was, well, let's just try caching it for 5 seconds. So both within our code, 5 seconds, both our application, like event pages, code HTML we generate, let's try caching it for 5 seconds. It's a trade-off. Like people can see stale data for 5 seconds, but that's such a short time window that that is probably okay. But once we wanted to get higher cache hit rates and move beyond that, we had to come up with more sophisticated ideas. For our calls within our service layer, we built out something that is pretty neat. I think it's a centralized invalidation logic. So we have a daemon that consumes the binary logs from MySQL, which is our primary data store with the canonical representation of anything within the system is stored. And this daemon understands that, hey, if a change to number of available tickets on an event page went through, there are these type of cached objects in Redis that I should go attempt to invalidate if they exist. So building out logic for each service that wants to cache whatever it's responsible for, whether it's tickets or venues or whatever else, to track the representation in MySQL and then build this one centralized place that can do the invalidation was helpful for us because otherwise, with our twisty mess of code base, there was concern that we wouldn't be invalidating things in the proper places when they were actually updated, and we would be caching and serving stale data, which would not be good. But with this centralized invalidation system, we were able to, over time, get confidence in it and ramp up to where we were actually caching things, I think, for some service calls where we actually got a good hit rate, as long as 12 hours. So that was a big win. And the other thing that was even newer and has been a really promising pattern for us is what I'm calling this wrapper strategy to allow us to have a dynamic TTL on pages. And this is something we've used in our HTTP caching layer. So in that layer, if we're just doing straight calls through Varnish to decide based on a URL if it should serve a cached response or not, that doesn't give us very much control, right? We can't write too crazy logic there. We can't really talk to any of our other data stores. We can't really understand, is it safe to cache this for longer or not? So what we've ended up doing instead is building both an inner and an outer version of some key pages, like our event pages. For our inner page, for the outer pages, this page is never actually cached. But it does a minimal amount of work. It's designed to be super fast. It's only doing really 2 things. The first thing it's doing is it's looking up some data in Redis, again, based on that sort of centralized bin log consuming process we talked about before. Like, when was the data that makes up this event page last updated? And the older this event page is, the longer I'm willing to cache it for. We think it's worth storing it in the cache. If it hasn't changed in a while, it's less likely to change in the future. But if the page was to change, because we're hitting this outer uncached page first, we would still pick that up quickly. The other thing the outer uncached page is doing is it's calculating a normalized version of a URL to represent that event page internally. So let's say you're an organizer on our site and you like advertise your event through different channels. Maybe you're like you own a music venue and you are using our Spotify integration so people can click through from Spotify and see like what concerts are going on in their area and land on Eventbrite. You would pass through an affiliate code there that we would want to, in our code, like process and track. And you might have other affiliate codes coming from Facebook and other places. Like in the past, we had problems where we were not caching as effectively as we could because we had different cache keys for each different affiliate code that came through. And we were actually missing data that our analysts cared about because guess what? When we did have a cache hit for that event page with the affiliate code, because it never hit our application code, it didn't get pushed through to our analytics logs, and the analysts realized they didn't have a lot of data to properly understand sort of the effectiveness of some of our sales channels. So they weren't happy. So the data engineering team wasn't happy. And then eventually just basically no one's happy and we have to fix it. So this outer event page, as part of the lightweight work it does, gets to take care of sort of like logging that analytics data and then sort of stripping it out. So when we make a request to the inner version of the page, it no longer has to carry about anything variable that doesn't actually affect the page contents, like those affiliate codes. And now the outer page that ran in the Django application code makes a request for the inner page. The user never sees this. That request for the inner page gets filled in by Varnish based on the contents of its cache. So kind of in some ways it feels like a Rube Goldberg system. And if I've explained it poorly, corner me afterwards, and I'll try again. But what this has let us do is for like really active events have better cache hit rates because we have that normalized cache key now. And for less active events, but that were still being requested by users or by bots crawling the site, actually have much better cache hit rates because they're still in the cache maybe an hour after they were last accessed instead of all being flushed out after 5 seconds. Finally, capacity planning. So this, I feel like, is actually fairly hard. It's hard in a way that's different from the other patterns I showed you. The other patterns, like as a general operator or developer, you can sort of figure out how to apply them based on knowledge you have. But to do this well, it helps if you have people who are actually comfortable with math and statistics. And it really helps if you're actually gathering the right data about the behavior of your systems and your applications. And so for us, we're not the greatest at this, but we try and do okay. There's a few things we do. One thing is load testing. It's very helpful to have an environment under which you can create load you understand and perform experiments. Like if I do X, I expect Y to happen. And oh, if it didn't happen, why is that? Let me go address the bottlenecks in the system. Let me understand how much work I can get done per unit that I want to scale up. And then have your production capacity be informed by the results you got from your load testing. The other thing is collecting those stats on your servers, on your application around throughput, around latency, around requests and queries, and look at the growth of that over time, and also look at the seasonality of that, which is an interesting component. So for us, that turns out to be things like we need to spin up more API servers on New Year's Eve because everyone goes out and checks into lots of New Year's Eve parties on the mobile application, like just on New Year's night and New Year's Day. Fun stuff like that falls out of it. So, to recap, at Eventbrite, we have a number of patterns we've adopted to ensure the capacity and stability of our systems, such as bulkheads, canary testing, graceful degradation, rate limiting, timeouts, load shedding, caching, and planning. So, I hope that I've given you some useful ideas for how you can take these and apply them in your own systems. If you want to learn more about this sort of stuff, here's a few books I would recommend. These are all quality. Some, like Release It, have whole sections dedicated just to working through examples and helping you figure out how to build and apply some of these patterns. Others, like Art of Scalability and just the rest through there, have good sections where they focus on this and put it in the context of like broader systems architecture or operational work. Thanks for listening. I gather I have a little time left. Yeah? So at this point, I am going to open it up to questions from the group. Yes, you first.
I was curious how often all those mitigation techniques and patterns that you were just talking about fail, and you actually have like a big customer outage that people see and talk about.
Yeah, so I probably shouldn't talk about that on camera.
Okay.
Find me later.
Okay.
Yes.
Can you repeat the question?
Yes, yes. Thanks for the reminder.
So do you have any tools that you use for testing application behaviors for timeouts and failures? Like Chaos Monkey or do something?
Yeah, actually, there's a few we've used a bit. This is something we're not as disciplined about as I feel like we should be. I think Varian might be one, if I'm getting the name right, that we can sort of like interject as a proxy in between requests and like force timeouts, force slower responses, and that people have tried that. There's also, and we do sometimes just apply strategies like, well, what happens if we used IP tables to drop a certain percentage of traffic or drop this service completely, and sort of like see how we handle that. Yeah. Yeah. So we are, your question is, do we own our infrastructure or do we use cloud hosting? We are at this point totally on AWS. Yeah, we have a primary site in US East and a DR site in US West. Do you want to follow up real quick?
Sure. Have you ever looked into any of the AWS Lambda stuff for alternative approach?
Not really in depth. There's some interesting strategies around services like Lambda, but we're more comfortable with some of the patterns we've been applying already. Yeah. Yes. Yeah, so that's a good question. So the question is, if you're building out a culture of like pervasive feature flagging, like how do you actually clean up your code base? Because it can be like quite confusing to have to code around all these flags, and you might not even understand are they still used or not. So that's generally up to the responsibility of the developers who have like the team that owns that feature. At a certain point, they'll feel like, we're not. It's been global for a while. We're not going to roll it back. So they'll do a code cleanup. We do have some tools that we like sort of attempt to determine if there's a dead feature flag and encourage people to look at those and see if they can be cleaned up. Because feature flagging is not without its downsides. Like I wouldn't want to work anywhere that didn't do this again, but it does make some of the coding more difficult for sure, and also makes just like integration testing, for instance, more complicated. You have to think about the different scenarios and flag states. Hey, sorry.
One, for your question on feature flags, in our experience, we found that if we structure the code so the flag is the first primary chunk of code, and that the old behavior is the else condition or the default, when you go to make a flag, the definitive rule, basically just going through deleting all the else's, right? And it puts the prominent code up front for other developers to hit at the top instead of at the bottom of the new code that other developers should keep in mind when they're working should be the good flag. So it's just kind of mentally making it's not the option, it's actually the default. It's not quite there yet. Has helped mentally do that. But you mentioned again, you guys use feature flags so heavily. What testing strategies do you have that pages don't become unusable, CSS or JavaScript don't fall out in strange ways in behavior, and you're automatically flipping flags back and forth and QAing that work at all?
So, I'm not absolutely the best person to answer a question around like how do we test that like flag changes don't like break like user visible behavior. The basic answer is that there's a lot of manual QA and test plan development that would go into like user-facing flag features, and so people would be testing different conditions and sort of different scenarios. But I would be lying if I didn't say that like in the past when there's been like really intensive development across teams in a few areas, that has gotten a lot trickier, and we haven't had a good sort of like automated testing strategy around it, which means that you do rely more on the human testing strategy and things can slip through.
It's something we struggle with flags, love flags, but like you say, you have lots of combinations
Yes.
Do you bake any analytics into your feature flagging infrastructure to see how often else cases are being hit, or which feature flags are being most used, or stuff like that? To tell you you should turn them off because hey, the else is never being hit.
So the question was do we have any analytics in our flags to tell them when certain conditions are being hit to understand if they should be cleaned up or not? And for the way we use the flags, generally I don't think that is applicable or helpful. Maybe you could explain it to me more later what you're thinking. But generally we're setting things in, particularly for a feature ramp up, in such a way that we understand. If we're saying if we want 50% of users to get variant A, 50% to get variant B, then we sort of know that level. It's not a flag in which a condition isn't selective in a way where we don't understand what the intended behavior is going to be. Yeah.
How do you handle outages outside of core working hours? Do you have an on-call schedule, or do you have a team working?
Yeah. So the question is how do we handle outages? Things can go wrong 24 hours a day. I'm not awake 24 hours a day to answer all of them, right? That would also be terrible. So right now we do have team members on my team, the systems engineering team, who are in an on-call rotation for the entire infrastructure. We are in different time zones, but not too different. So for us, the way we tend to do it is we'll have 1-week rotations where I'll be on call for 168 hours, and then someone else will be on call. Generally, things aren't failing left and right. We're a fairly mature company, good processes, good infrastructure. But yeah, things do go bump in the night, and then someone has to wake up. Are there other questions? Are there any hands I'm missing? Yeah. Yeah, that's a great question. So the question is if we want to learn more about how Eventbrite does this, are there resources we've published? We do have an engineering blog, which has some good posts, actually great Python posts. I think someone's been doing a series on how we're redoing our Python packaging and distribution internally recently. But to be honest, I don't think we've published a lot on this. So this talk and the video is going to be probably the main public resource. If you want to talk to me more about things and there's ideas spring around in your head, find me. And the other thing I would say is, although Eventbrite, is in a business where we have to deal with this, lots of companies are, and that these books really are great resources to draw on. Yeah, we didn't invent all this stuff ourselves. The parts we did invent, maybe we shouldn't have. Well, it looks like that's it. So thanks again. This has been a lot of fun. And find me. Yeah. And if I open that up, probably everyone would say that's really what they want. Cool. So, hi, I am Brian Pitts. I work as a systems engineer at Eventbrite in our Nashville office. So I drove up yesterday. This is my first time at Pi, Ohio, and first time in Columbus as an adult. It's been wonderful so far. I'm really looking forward to the rest of the conference and getting to know you and this great city more. So I am Skyrus on Twitter, if you're the sort of person who likes to follow people on Twitter. And I have a website at Polybyte where you'll be able to find these slides after the presentation. So I work as a systems engineer. What does that mean? So what does systems in here mean? So this is an unweighted visualization of software that I took by looking at our configuration management repo and pulling it all out. So this is what powers Eventbrite, and it's a lot of stuff. And my team basically is responsible for the care and feeding of all of these systems and infrastructure. Hopefully there's at least a few things on there that might look familiar, like Python. Right.
Okay. Hey, good morning, everyone. Thank you for coming. We're going to kick it off this morning with capacity and stability patterns presented by Brian Pitts. Welcome him on stage.
Hey, so thanks a lot for that introduction. This is going to be a talk on capacity and stability patterns. But before we get into that or get into me, I'd like to ask a few questions and get a show of hands so I kind of have a feel for the audience I'm talking to today. How many people here consider themselves to be primarily software developers? Cool, so most of the room. How many people would say they're primarily systems administrators or operators? All right, a few of us are represented here. How many people don't fall into either of these groups but just want the websites you use to actually work? So a big part of the job for the operators and developers at Eventbrite is designing systems that can cope with this sort of traffic pattern. Now, we are far from perfect at doing this, and this presentation I'm going to give you is far from comprehensive about ways you can tackle this problem. But my hope is that I'm going to give you some concrete ideas you can take to improve your own systems that you're developing and operating. And the patterns I'm going to talk about today generally fall into one of two categories. The first of those is stability, which I'm defining as doing processing, doing work in the face of impulses, stresses, or component failures. And I said this is how I'm defining it, but actually I'm cheating. This is from Michael Nygaard's book, Release It, which is a fantastic book and one of several that I'll recommend throughout the presentation. So in his definition, an impulse is a rapid shock to the system. It's that hockey stick graph that just is chugging along and then goes up, up, up when that event goes on sale. And stress is force applied to a system over time. So maybe that data store you're using that's on a bad disk and has suddenly started dropping in performance by 10%. What's the effect of that over time? So stability is number one. The second category is capacity. And this capacity is the throughput a system can sustain with acceptable response time. And accessible is a key point here. When I've given this talk before, I've got questions about, well, how do you define capacity? I can throw, 100,000 requests at the system, and they'll come through. But that's not a good way to measure your throughput if that first request only comes through after processing for 5 minutes because you've saturated your resources, and all your users are long gone by then. So it doesn't matter that technically you could sustain 100,000 requests a minute if all of those requests are going to a browser that's already disconnected. So now I'm going to dive into some of the patterns that we've applied here. And after each pattern, this is in the past I've had Century, Whiskey. If Django's not on there, it should be in big, bold letters, because Eventbrite is primarily a Python and primarily a Django shop. Now, what about Eventbrite? The fun thing about talking at tech conferences, I usually don't have to introduce Eventbrite, because if you don't know what Eventbrite is, how did you get your ticket? How did they let you in the door? So we call ourselves as a global marketplace for live events, which is big ambitions. In the last year, we had 600,000 active event organizers, sold over 150 million tickets, and did $2 billion in revenue from those ticket sales. Now, here's the interesting thing about events. Some events are bigger than others. This is a graph of calls to one service endpoint involved in purchasing a ticket. And in Eventbrite vernacular, this shows what we call an on-sale. Just like a sudden, extreme spike in activity due to a popular event going on sale.